Among the many fundamental questions that concern humanity, such as the origin of life, the nature of consciousness, the mysteries of dark matter and energy, and the essence of gravity, one key question stands out: how did it all begin? Despite the continuous development and increasing complexity of existing theories, the origin of the universe remains shrouded in many mysteries. This work attempts a detailed examination of our current understanding of the universe's first moments and its subsequent evolution. We will seek answers to questions such as the causes of the universe's expansion and why this expansion does not affect objects around us. Does the universe have a center, and if so, where is it located? We will also explore the structure of the largest formations created by the universe and the Milky Way galaxy's place within that structure. Furthermore, the most popular alternative theories to the Big Bang will be analyzed, including their rationale and potential to become the leading explanation for cosmic history. Prepare for a deep dive into the universe's profoundest secrets. Currently, most scientists agree that the universe, in its present form, originated about 13.8 billion years ago from a massive event known as the Big Expansion. This event marked the beginning of all energy and matter and established the physical laws that govern the universe to this day. The Big Bang Theory, ironically named by one of its early critics, is the most widespread and accepted explanation for the beginning of everything. Substantial and compelling evidence supports this theory. Specifically, it is known that the universe is expanding, and this expansion is accelerating. Additionally, scientists have detected the thermal imprint of the Big Bang, known as the cosmic microwave background. According to the traditional Big Bang theory, the universe began as a point of infinite density and temperature, whose nature is not fully understood. This tiny, dense object contained the energy of everything that has ever existed, albeit in a different form. Unfortunately, very little is known about the state of matter at such an early stage. Nevertheless, this point contained all space and time. Scientists call this moment the singularity. Attempts to imagine this all-encompassing object may prove futile, as our minds tend to place it in a specific region of space at a particular moment in time. However, one should not search for the singularity's location, as there was no place to put it yet. Nor should one speak of what existed before the Big Bang, as the concept of time, of before, did not yet exist. All of this emerged as a result of the Big Bang. The singularity represents the first unresolved problem of the Big Bang theory, as the existence of an object with such unusual properties sounds paradoxical in itself. Infinite density and temperature in finite time indicate that general relativity, on which this theory is based, is not the best description of physical laws at that moment. Many scientists believe that without considering the effects of quantum mechanics, it would be erroneous to describe the events that occurred then. Thus, until a unified quantum theory of gravity exists, the initial singularity remains a complex topic to understand, and most alternative models of the universe's evolution primarily seek to avoid its existence. Ultimately, knowledge of the universe's very first moments is currently limited to many assumptions. The absence of astronomical observations that could confirm or refute existing theories creates additional difficulties. However, based on the extrapolation of space expansion, physicists hypothesize that the most fundamental processes in the universe occurred within the first trillionths of a second of its existence. For example, when the universe was 10 superscript 3 seconds old, it was the hottest and densest in its history. This period is called the Planck epoch, named after the smallest measurement scale in particle physics. At this stage, the four fundamental forces of the universe, electromagnetic, strong and weak nuclear forces, and gravity, were unified into one. A more detailed description of this period requires the creation of a unified quantum theory of gravity. Following the Planck epoch came the Grand Unification epoch, which lasted only a few billionths of a second. During this period, the universe's temperature dropped sufficiently for gravity to separate from the other fundamental forces. The electromagnetic, strong, and weak interactions remained unified in what is called the electroweak force. Quantum effects gradually weakened, and the laws of general relativity began to dominate. Approximately an infinitesimally small interval of time, around 10 superscript 3 seconds after the Big Bang, a phase transition occurred, fundamentally changing the state of matter. This event, known in the scientific community as cosmic inflation, marked a period when the universe began to expand at an incredible speed, theoretically not even limited by the speed of light. This period, though extremely short, was filled with dramatic changes. The universe's volume increased by countless magnitudes in fractions of a second. At first glance, inflation might seem to contradict special relativity, which states that information or matter cannot travel faster than the speed of light. However, if inflation indeed occurred, it was space itself that expanded, not matter, which does not conflict with the mathematical principles of relativity. In this early epoch, the universe was predominantly filled with radiation, but the first elementary particles, such as quarks, electrons, and neutrinos, had already begun to form. It is worth noting that the concept of inflation, proposed in the 1980s, was intended to resolve some problems arising within the Big Bang theory. Despite its popularity, the Big Bang theory could not explain why the universe appeared so flat and homogeneous, and why its different parts began to expand simultaneously. Alan Guth proposed that if a physical field, called the inflaton field, existed in the early universe, it could have caused the universe's accelerated expansion. It soon became clear that such expansion could eliminate many shortcomings of the Big Bang theory. The idea is that the inflaton field possesses enormous potential energy. When the field changes its state, for example, decaying into normal vacuum, all this potential energy is released, leading to a rapid expansion of space. This mysterious energy must have smoothed out and accelerated the universe's expansion in such a way that we observe it as flat and homogeneous today. It is important not to confuse the inflaton field with dark energy, which is currently accelerating the universe's expansion. Before dark energy began to dominate, the universe still had nearly 8 billion years of evolution to undergo. However, inflation did not last long, and after its completion, the universe continued to expand, but much more slowly. The question of whether the inflaton field truly caused this brief but rapid expansion, and why it suddenly stopped, remains one of the key questions in cosmology. Because the inflation model postulates the existence of some mysterious form of energy in the early universe, and due to the impossibility of directly verifying this theory, inflation is a subject of debate and not supported by all scientists. Nevertheless, today it is considered the leading theory for explaining the universe's characteristics, particularly its relative flatness and homogeneity. This is our best attempt to explain why approximately the same amount of matter is uniformly distributed in all directions. Many scientists believe that it was during inflation that microscopic quantum fluctuations formed the seeds that later shaped the universe's large-scale structure. After inflation, all the building material of the universe was a quark-gluon plasma. What is that? Plasma is a state of matter where the temperature is so high that electrons cannot combine with nuclei into atoms, but exist separately, forming a new form of matter. The most famous example of plasma is lightning. Quark-gluon plasma is a state where the temperature is so high that even the constituents of protons and neutrons, quarks and gluons, cannot be held together. In other words, it is the temperature at which protons and neutrons literally melt. These were the conditions that existed in the early universe. In this incredibly dense and hot soup, pairs of elementary particles and antiparticles of all kinds were formed: quark-antiquark, electron-positron, and so on. All of them inevitably collided with each other, leading to their annihilation, or mutual destruction. However, perhaps at some point, an unknown reaction occurred that disturbed the balance between the amount of matter and antimatter. One of the most important problems in modern physics is the predominance of matter over antimatter in the universe. In the modern cosmos, we observe almost exclusively ordinary matter. However, cosmological models for the formation of elementary particles suggest that the amount of ordinary matter in the universe should be zero, as matter and antimatter should be created in equal quantities and ultimately destroy each other. Nevertheless, we see that this balance was disturbed for some reason. For example, the number of quarks and leptons exceeded the number of antiquarks and antileptons by approximately 1 particle for every 30 million. As a result, in the modern universe, there is more matter than antimatter. As cosmic expansion unfolded, temperatures and pressure in the young universe steadily declined. Approximately an infinitesimal fraction of a second, specifically 10 superscript 1 superscript 1 seconds, after the Big Bang, a clearer picture of events begins to emerge for scientists. The energy levels of particles reached values that could be reproduced in laboratory conditions using accelerators, paving the way for their detailed study. Approximately a billionth of a second after the Big Bang, elementary particles, quarks and gluons, began to combine, forming protons and neutrons, the building blocks of atomic nuclei. Thanks to a slight excess of quarks over antiquarks, the number of protons and neutrons exceeded that of their antiparticles, antiprotons and antineutrons. However, as the cosmos expanded, the temperature continued to fall, reaching a critical point where there was no longer enough energy to create new proton-antiproton or neutron-antineutron pairs. As a result, previously formed particles underwent annihilation, leaving behind only one proton and neutron for every 100 million particles, and completely destroying antiparticles. A similar process occurred with electrons and positrons approximately 1 second after the Big Bang. After this massive annihilation, neutrinos finally decoupled from the plasma of charged particles and began to move freely in space, while photons continued to interact actively with the plasma. A few more agonizing minutes passed. When the temperature dropped to approximately 1 billion degrees Kelvin and the energy density decreased, protons and neutrons began to combine, forming the universe's first nuclei of light elements: hydrogen, helium, and lithium. This period is called Big Bang nucleosynthesis. Protons, being less massive, proved more stable than neutrons, whose half-life is only 15 minutes. Less massive protons, according to current understanding, may be virtually eternal. Consequently, in the process of particle combination, there were more long-lived protons than neutrons. Many protons remained solitary, not forming a pair with a neutron. This is why hydrogen, whose nucleus consists of a single proton, makes up about 74% of all ordinary matter in the universe. Approximately 379,000 years after the Big Bang, the primordial soup of particles cooled enough for electrons to interact with nuclei, forming complete atoms, primarily hydrogen atoms. The formation of hydrogen marked a turning point in the universe's evolution, fundamentally changing the interaction between matter and radiation. Certain types of radiation were suddenly freed, and photons began to propagate unimpeded throughout the universe. This sudden event allowed the thermal glow of the plasma, which existed immediately before hydrogen formation, to radiate throughout the universe without any interference. The cosmic microwave background radiation, detected in 1965 by Arno Penzias and Robert Woodrow Wilson, who were awarded the Nobel Prize for this discovery, represents a kind of snapshot of the universe at 380,000 years old after the Big Bang. This is the oldest light in the universe, serving as an invaluable tool for cosmologists, and the primary evidence for the Big Bang theory. However, after this first light, no other radiation sources yet existed, and the universe plunged into an era of cosmic dark ages, lasting hundreds of millions of years. Nevertheless, important processes occurred during this period. Denser regions of almost uniformly distributed matter began to gravitationally attract each other, forming the seeds of galaxies. Within these proto-galaxies, matter continued to contract until pressure and temperature reached the values necessary to ignite thermonuclear fusion. This is how the first stars were born, illuminating the universe. Theoretical calculations show that these stars were tens to hundreds of times more massive than the Sun and emitted millions of times more light, yet their existence was fleeting, only a few million years, after which they exploded as supernovae. They emitted harsh ultraviolet radiation, which split most of the hydrogen back into protons and electrons. This process is called reionization. Ionized hydrogen, unlike neutral hydrogen, is transparent to radiation, allowing starlight to propagate freely in space. For a period, the star's harsh radiation gradually ionized an increasing portion of the hydrogen around them, forming bubble-like regions of ionized plasma that grew and merged. As more and more of the universe became ionized, light of various wavelengths could freely escape early galaxies, revealing the distant universe that we observe today with modern telescopes. In the vast expanse of space, stars continued their tireless work, forging heavy elements from hydrogen and helium in their cores. And then, at the end of their lives, they exploded as supernovae, scattering these newly formed elements throughout the universe, like seeds from which new celestial bodies, such as planets, would later grow. In essence, our Earth owes its birth to these stellar forges, where the elements that compose it were created. Today, approximately 13.8 billion years after the Big Bang, we observe a cold cosmos that continues to expand, and at an accelerating rate, similar to what occurred during the inflation epoch, though orders of magnitude slower. A natural question arises. If the universe is expanding and distant galaxies are moving away from us at an accelerating rate, does this mean we are at the very center of this expansion, like in the middle of a giant bubble? This question has intrigued humanity long before the discovery of expansion and the Big Bang theory. Since their appearance, gazing at the starry sky, people intuitively believed that everything revolved around them. For millennia, Earth was considered the center of the cosmos, around which the Sun and other planets orbited. However, over time, it became clear that we are not even at the center of our solar system, which, in turn, is lost on the outskirts of an unremarkable galaxy. Edwin Hubble's discovery in 1929 was a true revelation. The speed of distant galaxies indicated that the farther they were from us, the faster they receded. It is no wonder that this created the illusion that we are at the center of an expanding universe. But this is not the case. Moreover, it is quite likely that the universe has no center at all. To understand the nature of the universe's expansion, it is necessary to grasp one simple yet complex truth. The Big Bang is not an explosion in the usual sense of the word. We should thank Fred Hoyle for this name, although it is more misleading than it is descriptive of the phenomenon. Most people, upon hearing the phrase, Big Bang, instinctively imagine something akin to an ordinary explosion, and the expansion of the universe as scattering fragments. And while all matter and energy were indeed in an extremely hot and dense state, and then cooled as they expanded, this does not mean one should imagine an explosion. The Big Bang is neither big nor an explosion. An ordinary explosion always begins at a specific point in space. But the key idea is that the Big Bang did not happen in space. It was the expansion of space itself, which was created during the Big Bang. Therefore, it is meaningless to look for the location of the explosion in a space that did not yet exist. The expansion occurred throughout the entire universe simultaneously, everywhere. In every point of the cosmos, the Big Bang happened. Initially, the distances between objects were extremely small, but over time, they increased. In other words, the Big Bang is the distribution of all matter and energy with the expansion of space, and this distribution has nothing in common with an ordinary explosion. During an ordinary explosion, lighter particles travel farther than massive ones, as they require less energy to move. As a result, at the fringes of an explosion, the density of matter and energy decreases, and the center of the explosion can be easily determined by measuring the particles' trajectories and calculating their initial position. But this is not observed in the universe. It looks the same in all directions and at all distances, with roughly the same density of matter and energy, and an average number of galaxies. The universe shows no signs of an ordinary explosion. Having clarified the term explosion, let's try to understand the expansion of space, which our brain often misinterprets. So, we know that the universe is expanding because we observe distant galaxies receding from us. The exception is Andromeda, which is, on the contrary, moving towards us. More on that later. For now, let's focus on distant galaxies and their movement, as this is crucial for understanding the expansion effect. The farther away galaxies are from us, the faster they recede. And this is probably the main reason why people believe we are at the center of the universe. It seems that if you rewind time, all these receding galaxies should just fall onto us. But this is not the case. We are not at the center of the universe. Like it or not, we do not have such a special planet or galaxy. Most likely, the concept of a center of the universe simply does not exist. In the boundless expanse of the cosmos, a phenomenon of galaxies moving apart is observed, as if all of them are striving to move away from each other. However, as science notes, this phenomenon is a natural consequence of the expansion of the universe itself. The only exceptions are galaxies within local groups, whose gravitational bond currently resists the universal separation. The essence of the universe's expansion lies not in the creation of new matter or the emergence of additional universes, but in the increase of space between already existing objects. Imagine cosmic space as a fabric that stretches, increasing the distances between galaxies. This is why it appears to an observer on Earth that all galaxies are moving away from us. However, if we were to move to another galaxy, we would see a similar picture, all other galaxies moving apart, as if we were once again at the center of the universe. For illustration, one can imagine an animation. Our galaxy is at the center, and all other galaxies are moving away from it. For example, at a speed of 5,000 kilometers per second, galaxies twice as far away move twice as fast, at 10,000 kilometers per second. If humanity developed intergalactic travel technology and found itself in another galaxy, we would see the Milky Way moving away from us at 5,000